Welcome to another video in our course of probability theory. We are in the middle of the convergence results, and today we're going to talk about Lévy's continuity theorem. Assume you have a sequence of probability measures and you know their characteristic functions. Assume also that they converge to some other function which is, let's say, continuous. Do we then already have something like the convergence to some probability measure which has the limiting function as a characteristic function? The answer is yes, and that's the topic of Lévy's continuity theorem. So it builds a connection between convergence of characteristic functions and weak convergence. Let's see what that all means. So, Lévy's theorem. Let's get started. First, we need to find a connection between weak convergence and a separating class of functions, which you might remember from the last video. So just to recall, a separating class of functions was like this here. M is separating if whenever P is not equal to Q, then there is some F such that P and Q have different integrals with respect to this F. So the following are equivalent. So Pn converges to P, and Pn is tight. Remember this from the other video, I guess, was it here? Let's see, that was the introduction to weak convergence. Probably that's wrong because it was in number 11. Yes, I guess it was in number 11, which I just have not opened. So let me write it down. So what does tight mean? It means that for all epsilon bigger than 0, there is a K compact such that zoop Pn on the K, or on the so the maximal amount of mass the Pn's put on the complement of K is smaller than epsilon. So we also had with Pohoff's theorem that tightness is the same as relative compactness. And relative compactness means, well, the closure is compact, or every sequence has a convergent subsequence. That's what we are going to need. So tightness is easier to check than relative compactness, and Pohoff's theorem tells us it's the same. So with this here, we have every sequence has a convergent subsequence. And well, these two apparently are not the same because, okay, weak convergence implies tightness because every sequence has the same convergent subsequence. But from tightness, we never have convergence. We need something in order to show convergence. And this is, well, P and F converges to PF for all F in the separating class of functions. So not all continuous bounded functions, but only on this separating class of functions. Okay, from 1 to 2, I say I don't have to prove anything. That's clear, because if you have V convergence, you have that every subsequence has a convergent subsequence, which is the same as being tight. And this here, of course, also holds because that's part of weak convergence. Okay, then the other thing from 2 to 1. Let's do like this. we assume that 2 holds, but 1 does not hold. And we have to find a contradiction, and then we have proved that 2 implies 1. Since 2 holds, since 1 does not hold, there is some epsilon and some continuous bounded f and some sequence n, well, let's say n1, n2, and so on, such that Pnf, not fk, but f minus pf is bigger than epsilon. Okay, we have that 1 does not hold. That means V convergence does not hold, so there must be one f where we can see that V convergence does not hold. So that means this here. On the other hand, since 2 holds, Pn is tight, so there is so this sequence here has a convergent subsequence. So there's a Q and NK1, NK2, and so on, such that Pn converges, KL converges as L goes to infinity to some Q. Then we have on the one hand side that P integrated with respect to this F here that we took here, minus Q integrated with respect to this F here. When you look at that like this here, I forgot a K here. So PNKF converges to this here. So all these are bigger than epsilon, and the limit of this here is Q. That means that this here is bigger than epsilon. On the other hand, we have that we have that for all G in M in the separating class of functions, PG so what do we have? Yeah, we have that 2 holds, which means that this here holds, which means P integrated with respect to G as the limit P N K L, like this here. This here must be also Q integrated with respect to J, to G, because the PNKL converges to Q. That means P and Q agree on all G in M. And since the class here is separating, the last thing here implies P equals Q, whereas of course this line here implies that P does not equal Q. So we have a contradiction because we have shown P not equal Q and P equals Q, which means we have shown that 2 implies also 1. And that was it. Okay. Next. We have to make a connection now between tightness, which has something to do with the mass outside some compact set. And this here is, well, a generic thing outside a compact set. So close to minus infinity and close to infinity, and the union of this. on the one hand side. On the other hand, the characteristic function, which plays a role here. And I forgot to delete this here. We do not need this here. Okay, so let's prove this. Yeah, so take any positive c and take some x which has distribution p, such that we can write that this here is the expectation of e to the itx. Then let's start on the right hand side and replace the 2 over r by some c. 1 minus psi p of t dt. Let's replace the characteristic function by its definition. 1 minus e to the itx dt. So that was just the definition of this here, and exchanging the integral like this, exactly. We can integrate this because integrating 1 from minus c to c gives a 2c, and integrating e to the itx gives us a 1 over ix e to the itx, and that from t equals minus c to c, and the expectation here, like so. Then we see, okay, e to the itx, what is this? That's the cosine of tx plus I times the sine of tx. But the cosine vanishes because we're using here t equals minus c and c, and the cosine is symmetric. So the sine stays. Yes, and we have the sine of tx times I. The I vanishes here. And let me write it like this. 2c and the I here. Then I need to write 2c here because this 2c times 2c, this 2c gives a 1. And I have from here the sine of tix, sine of tix, sorry, ti is just a variable which I need to plug in here, cx divided by this x here. And I need to have this 2 times because I have the upper and the lower end of the integral, which means I can just get rid of this 2 here, and that's it. Apparently, this is larger than 2cp 1 minus sine cx divided by cx. Remember that this here is smaller than 1, which means that this here is bigger than 0. So if I restrict this here to the set that cx is bigger or equal to 2, I make that smaller, which is the reason for this inequality here. Yes. So like this. And apparently I have a bound here. I have a bound here, exactly. So this here is smaller than, so I have c times x is bigger than 2.
that's bigger than 2. So this here is bigger than 2 and sine is smaller than 1, which means here that the whole thing here is bigger or equal than half. Like this. So it's bigger or equal than c times probability that sine x bigger or equal than 2. Well, so that's p of, so c times p of minus 2 over c well, x smaller or less than minus 2 over c or x bigger than 2 over c, like this, which is exactly this here if we choose c to be 2 over r. So if c is 2 over r, this here is minus r and it's r. So it's exactly this set here on this side. And I have the c here, which I can multiply to the other side. C is 2 over r, so r over 2, which is this one here. And I have the c, and the minus c is 2 over r minus 2 over r here, and that's exactly the result that we want to have. Okay, that was a lemma, which we're going to need. And that's another lemma that we are going to need. Uniform continuity, that's okay, it's a basic lemma, which you might also know already from your calculus class. A set of functions is called uniformly continuous in some x if, well, whenever y converges to x, that goes to 0, so f of y minus f of x goes to 0, for all, so uniformly for all f in the set of functions. And there is a basic result on this. So if fn converges to f, and fn, the set here is uniformly continuous in 0, then the limit is continuous in 0. On the other hand, if it's continuous in 0, then we also have that the sequence is uniformly continuous. Let's prove that real quick. So we have two directions from right to left. So f of t minus f of 0. What do we need to show? So we need to show if t goes to 0 that this here converges to 0. On the one hand, this here by uniformly continuity, and fn converges to f. Since fn converges to f, that's the same as lim sup fn of t minus fn of 0, apparently. But we know if t goes to 0, which means that here's the same as y goes to x, so this here converges as t goes to 0 to 0. Which means we have shown that f is continuous in 0. The other direction, if f is continuous in 0, then we have uniform continuity. How does this work? So we need to show uniform continuity. Okay, for sequences I can replace the sup here by the lim sup. Lim sup n goes to infinity, fn of t minus fn of 0 is less or equal than, well, I have to do something here. Lim sup, I have fn of t minus f of t plus f of t minus f of 0 plus f of 0 minus fn of 0. Like this, apparently. And recall we have continuity at 0. So if n goes to infinity, so this here converges to f of t, which means that, well, this here goes to 0. F of t minus f of 0. But we have continuity of f at 0. That means for t goes to 0, this here converges to 0, which shows the other direction, which we are also going to need in a moment. Because now we can put something together by using the uniform continuity on characteristic functions. And we have the following: if the characteristic functions of a family of probability measures is uniformly continuous, then we have that the family is tight. And tightness is something which will play a role in Lévy's continuity theorem. Okay. Uniform continuity of the characteristic functions, what does that mean? That means that the sup over all elements in the family, 1 minus psi pi I of t, for t to 0 to 0. Sorry, I was wrong. I know this here by the assumed uniform continuity here. That's exactly what this here means, at 0. And the 1 minus, okay, that applies to all here, so that doesn't change the uniform continuity. And as t goes to 0, the psi of 0 for all these characteristic functions, that's an expectation of 1, which is 1, and 1 minus 1 is 0, so that converges to 0. Okay, we have this. And we need to show tightness, and we are going to use this calculation here, which we did 2 slides ago. So if I have pi I of minus r to r, and we need to see that uniformly this here has large mass, if r is large, and this probability is bigger or equal than 1 minus the complement, which is minus infinity to minus r and r to infinity, which we bounded here by smaller equal. By the minus we have bigger or equal. Then the result I just write down, minus 2 over r, 2 over r, 1 minus psi pi I of t dt. So that's exactly the result that we had. I can make that smaller by subtracting more. And when I subtract more, when I put here the absolute values, 1 minus r over 2 minus 2 over r, 2 over r, 1 minus psi pi I of t dt. And this here, as we just saw, that's close to 0, which means that this here will here converge to 1. But how exactly? So we have here the infimum over all I, the supremum over all r, or let's just do this here, inf over all I, because it means we have the supremum over all I. We have here the supreme, but we make it bigger by saying the supreme is in here. So this here converges to 0 uniformly. yeah, so I have the supremum here, that is, if t becomes small, that's small. So I can do that, have that as small as I like. But then r goes to infinity. The whole integral here goes to 0, and I get 1. Okay. And that means I have tightness, because most mass, as r goes to infinity, is carried on this compact set minus r to r. And now we have everything together in order to state and prove Lévy's continuity theorem, which is the following. We have probability measures, we have a limit, and these converge pointwise. And we know that the limit function is continuous in 0. And the result is then Pn converges weakly to some p with the characteristic function, which was the limit that we had here. And the proof is now, since we did all the previous work, just an application. We have convergence here, and we have that limit is continuous. And like here, we have convergence, and the limit is continuous. Then we know uniform continuity of all these here. And because of this proposition, they're uniform continuous, then the corresponding probability measures are tight. So I know that the Pn, n1, 2, and so on, they are tight by this continuity here. Yeah. And we also had the other result. Yeah. So these two here are the same. I need tightness, and I need convergence along some f here. And that means I have convergence. So how do I get that? I have tightness. And since I have tightness, I know that there is a convergent subsequence. So I have some subsequence p and k, which converges to some p, as k goes to infinity. And now I have this. And since the characteristic functions is based on bounded continuous functions, I have that psi p and k of t converges to psi p of t for all t in R on the one hand side. On the other hand, it converges also to psi of t by assumption, like here. And that means that these two functions must agree. And we have found a p such that the limiting function is the characteristic function of this p here. What else? Yeah, and that's it. I think we have proved everything. We have proved everything, yes. So we have proved tightness, and we have shown that characteristic functions converge to the characteristic function of some p here. And that means by the other result that we had at the very start here, that's a wrong arrow. It must be a single arrow. This here is the convergence of characteristic functions. That means we have B convergence as here. And that's Lévy's continuity theorem. And let me also mention that the same holds. Okay, that's the other slide here. When we replace the characteristic function by the Laplace transform. but I will not show this here. Let's see one application, and or two applications. One, the theorem of Dumois-Laplace, and the other one, the convergence of geometric to exponential distribution. So yeah, let me do the harder thing here, and the other one maybe you can look at yourself. So the harder one is this one here. So that's a 5-line proof of the theorem of Dumois-Laplace, which states, so Sn is Bnp distributed, which means that its characteristic function, okay, that's k choose n, p to the k, q to the n minus k times e to the 1 y I t k. And this one here I can also hide here, p times e to the it to the power of k. And this here I can use the binomial theorem. That's q plus p times e to the it to the power of n. So that's important. And the result states that we have this convergence here. So we normalize the Sn here. And that converges to a normal distribution, which has, as you might remember, a characteristic function, which is e to the minus t squared over 2. And we're going to show in this calculation that the characteristic function of the Sn star, here the normalized version of the binomial distribution, converges to the characteristic function of the normal distribution. Okay, one has to be a bit careful about all terms here. So, well, so apparently this here is the same as, let's first of all say q is 1 minus p, as often. So that's Sn divided by square root of npq minus, and np divided by this here is square root of np divided by q, like this. And the latter term does not have anything random in it. And I can pull out of the characteristic function. And this here means I evaluate the characteristic function at a point not t, but t divided by square root of npq, like so. This characteristic function I just computed. That's this. And the term before, I can try to pull into this product of n same functions. I'm doing this by saying I have to do this to the power of 1 over n, which means essentially this square root of n in the numerator becomes the square root of n in the denominator, as here in one term. And in the other term I have this pi here, e to the power it divided by square root npq from here, and here I to the minus it, p divided by nq, p divided by nq, which I could also write as, well, p squared divided by pq, like so. Then we have the same denominator, square root npq, and I have pi square, square root of pi square, which is pi with a minus here, and I have 1 here, and a 1 minus pi is apparently a q, and a q divided by square root of q is this square root of q here, divided by square root of np. That's what I just write from here, like so. Now I have something to the power of n, and I need to see, so I have n's and square roots of n here. I need to see which things stay and which things become too small. So n is big, that means that this here is essentially 1, and q plus p equals this 1 here. And what remains is, well, first term from the Taylor series expansion of this exponential here, minus qit square root, then a square of this, half, by the second thing. The square is plus I square, which is a minus. Q I write down, t square, and the square root square is p over nq. That's this here. And the remaining term will be of order n to the 1 over n to the power 3/2. And from here I get the pi times, well, it squared q divided by np, okay. And by the squaring this I have a t squared half q divided by np, like so. And again, the remainder will be of the same order, which I can forget. Collecting terms, I get this 1 here. The square root of n's should disappear. So I have here q divided by square root of q, which is, well, square root of p times q. And the same happens here. Here I have minus, here a plus, so this vanishes. The terms with an n in the denominator, they do not go away, but we have one with a q and one with a p, so they combine to this thing here. And the rest is too small to play an effect. And the limit of this here is e to the minus t squared half, which is the thing that we wanted. Okay, and we did it. We already saw that Lévy's continuity theorem also holds for Laplace transforms. And here is yet another calculation showing that geometric distributions converge to an exponential distribution. So we already saw this using distribution functions earlier in the manuscript, and now we also have it for characteristic functions. So you can go through this calculation alone probably. Very nice. So we are done with today's video and hope to see you in the next one. Then we become more concrete in order to derive concrete limit results. See you then.